Hey-o! Good morning, everybody. All right, today we're going to talk about Chapter 33, Sections 4 and 5, which is polarization, reflection, and refraction. The first thing I want to talk about is to remind us about the electromagnetic wave. Remember, electromagnetic waves are waves that consist of both an electric field and a magnetic field. They're perpendicular to each other. They are coupled. They drive each other through their oscillations and then travel in a direction that's perpendicular to both the electric field and the magnetic field via the pointing vector, right? That's the E cross B. So in order to understand polarization, essentially what we're going to do is merely focus on the electric field. Okay, so for any light that is emitted from some source, it's going to have an electric field orientation. And for natural lights like the sun or stars and lots of things, those electric field orientations, the oscillation direction of the electric field can be in any orientation. It can be vertical, horizontal. It fills up actually all the angles. It's completely randomized. Okay. But what we're going to do is to depict unpolarized light. We're going to draw an electric field vertically and horizontally. Okay. This is essentially saying all of the components of the electric field oscillations are in randomized directions. Now, what polarization means is we get all of those electric field orientations all lined up in the same direction. Okay, and that can occur through a few different ways. But the one that we're going to talk about today is with a polarization sheet, okay, or what's called a polarizer. You may have heard of these with like polarized sunglasses. Okay, so a polarizer is merely, it's a sheet that's long chain polymers. It could be a film or something like that. And it has all those long chain polymers aligned in a particular direction. And any of the light that strikes that sheet, the orientations of the electric field that are aligned with the sheet, they pass through. And any of the orientations that are not aligned with the sheet, they get absorbed by the sheet itself. Okay, so it gives us a little bit of a tint, and it orients all of the electric field lines in a particular direction, whatever the polarizing direction of the sheet is. Okay, so there's actually a video in the description below. I'd like you to go check out. You can kind of see these things at work. Pause it right here and go check that video out. Okay, I'll wait. Okay, so now you've seen kind of how polarizers work. Let's talk about how we quantify the intensity of the light that comes through a polarizer. So imagine I have unpolarized light and it's traveling down this way and it strikes a polarizer with the orientation of the polarizer in the vertical direction. That light will strike this polarizer. All of the horizontal components of the electric field will be absorbed, and only the vertical components of the electric field will be allowed through. Okay, we can quantify this intensity of the light after it's gone through the polarizer by our 1/2 rule equation. The intensity of the light is going to be equal to the original intensity divided by 2. Okay, for one polarizing sheet, for unpolarized light only, the intensity of the light after the polarizer will be 1/2 of the initial intensity. Okay, this is our 1/2 rule. Okay, now imagine, like we saw in the video, we place a second polarizer after this first one. So we have unpolarized light. The first sheet orients the light all in one direction. It decreases the intensity by 1/2. And now we place a second polarizing sheet, right? At some angle. Let's call this angle, right? This is the angle between the vertical and the polarizing direction is some angle theta. The light that passes through this sheet, again, will be oriented in the direction of the polarizing sheet itself. But it will also have lost some of its intensity. We can calculate that intensity by our cosine squared rule. The cosine squared rule applies to originally polarized light only, and it's as follows. The intensity of the light is equal to the initial intensity times the cosine squared of theta. Theta being the angle between the polarized light and the direction of the polarizer, right? The polarizing direction of the sheet. That's our angle theta. Questions so far? Okay, the next thing I want to talk about is reflection and refraction. Okay, now imagine I have two different surfaces, all right? Let's say up here is air and down here is water. Now we know, or you've probably experienced yourself, that when light comes in and it strikes a surface, that it reflects. We're going to call this ray that comes down and strikes here, that's the incident ray, okay? And the angle that it makes with the vertical is called theta 1. It's the incident angle. Now, when that ray reflects off of the surface, it reflects off at an angle that's equal to the incident angle. We're going to call that theta 1 prime, and that is called the reflected angle, and this ray is the reflected ray. The law of reflection tells us that the incident angle theta 1 is equal to the reflected angle theta 1 prime. This is the law of reflection. Just like in billiards, right? You got to know your angles. The angle that it goes in is the same angle it comes out. Now there's another ray that's called the refracted ray. And the refracted ray is the light ray that goes into the other material. Now, the first thing we do before we get into refraction is talk about this concept of an index of refraction. So the index of refraction is the ratio of the speed of light in a vacuum over the speed of light in whatever material we're talking about, okay? So for instance, water, the speed of light in water is slightly less than the speed of light in a vacuum. So we get an index of refraction of water, which is something greater than 1. It's probably like 1.2 or 1.3, something like that. So we need to understand this index of refraction, because what happens is the light, when it enters from air or from a vacuum, it enters some other material, it actually slows down, and we can quantify that in the index of refraction. Okay, so we're going to set this incident area with an index of refraction N1, okay? N1 is the index of refraction of the material in which the incident ray exists. And it comes down and it strikes some other material. We're going to call that ray, or N2. It has index of refraction N2. This is the refracted material, the material into which the light is refracting. Now that refracted ray comes down and it makes some other angle with the vertical we're going to call theta 2. This is the refracted ray with the associated refracted angle theta 2. Now here's what the law of refraction states, that the index of refraction in the incident material times the sine of the incident angle theta 1 must be equal to the index of refraction in the refracting material times the sine of the refracted angle theta 2. This is the law of refraction, otherwise known as Snell's law, after some guy named Snell. Okay, so that's it for reflection and refraction. Okay, I want to talk about the incident angle and the refracted angle with an eye on the difference between the two indices of refraction. So imagine this. I want to solve for theta 2. Right? If I take this, I can say that, the sine of theta 2 is going to be equal to N1 over N2 times the sine of theta 1. So what this means is when N1 is less than N2, like in our example where we went from air to water, right? Air has an index of refraction of 1, water has an index of refraction greater than 1. When we do that, what we get is something that's less than 1 up here. So that would mean that theta 1 is greater than theta 2. What that means is if I have, here's my water, right? I get the incident angle, some large incident angle like this, then the refracted angle would be closer to that vertical. It would be something smaller than the incident ray. All right, what about the opposite? Say N1 was larger than N2, like you're going from the water to the air or from water to glass or something like that. Well, that would mean that theta 1 was less than theta 2. When you go from a larger index of refraction, let's say water, right, to glass, right, the incident ray has some angle, theta 1. The refracted ray bends away from that vertical. It's going to be a larger theta 2. Make sense? Okay, this lends me to a quick story I want to tell you guys. When I was a kid, a friend of mine and I would go out to, there was like this little peninsula of land that stuck out into a little pond that we had near my house. And it was kind of wooded, and we would go in there. I was probably, I don't know, 10 or 11 years old. And there's like a clearing at the end, and we'd have campfires and things. And there was this one little spot. If you crawled down towards the pond edge, this big fat catfish would sit right in this sort of in a little hollow at the bank of the water. And me and my friend, we got sticks and we sharpen them up, right, like spears, and we would go and we'd try to spear that fish, and always, to no avail, we would always miss. We never got the thing. And the reason is because we didn't understand the laws of refraction, right? So imagine this. Imagine the water is here. You know, you're up here, here you are, you got your spear, and you see the big catfish right down here, big old fish, right? Well, according to the law of refraction, remember, this is water, this is air. The light comes in from the sunshine, strikes the fish, and it's coming up to your eye. So the incident ray is down here. This is N1, here's N2. The incident ray comes up at some angle to the vertical, right? Here's our incident ray. And then it bends away from the normal because it's going from a larger index of refraction to a smaller index of refraction in the air. So a larger refraction angle. Okay, so I see that there. There's the eye. That's where I'm seeing the fish. But what that tells me is that really that ray coming up makes me think the fish is over here, right? This is the fake fish over here. There's the fish. So I'm always throwing my spear right at this fish, and I'm always gonna miss, okay? You gotta aim closer to where you think the fish is. So over the years, I just had to keep practicing, you know, and I've actually gotten pretty good at it. So I wanted to show you guys a little video of me doing some spearfishing just this past weekend. We're all in quarantine. You got to find stuff to do. So here it is. Check it out. All right. Well, I hope you guys enjoyed that. We'll do a sample problem next. Have a great day.